first order system of a mixing process. So I'm going to do the derivation using a tank containing a salt, a dissolved salt. So, so let us consider a simple a simple a simple example of what a first order what system of a mixing process. So before I come to that, I need to introduce the course code. Course code is K 301. That's the course title is process control. Process control. Process control is a course in chemical engineering. So I'm here to make a derivation, first order system of a mixing process. And when you are doing that, the derivation will come in such a way that the equation must come in this form: a1 dx over dt plus a2x equal to a function of that is k, a function of what t. So you are having a k multiplied by a function of t. So before we come to this equation, the derivation in this form, first of all we need to consider a tank. So we have a tank here, a tank. Now this tank contains dissolved salts. These are dissolved salts. So now let's assume that the salt moves with a volumetric flow rate, and at the same time we see that this salt is being transferred in a tank at a constant volume V. Let's say the volume of this tank now is V meter cube. So let's say that it's being transferred, it's coming in, it becomes the input. So, and then you have an output, the one that is going out. This is the output. Now let's say from the input we have a C1. Let's say it's a function of T. And this our C now, we call it density. And the density unit is what? In kilogram per meter cube. Meter cube. Then we also have the volumetric flow rate, Q. That's, let's say here is Q1 meter cube over what? X. That's the unit of this volumetric flow rate, is meter cube per seconds. So now, from here, let's assume that, let's say that the density of this tank here that contains a dissolved salt. Let's say the density is CO, and then let's say the volume of this tank is V meter cube. Now V now represents the volume of the tank. So now this C naught are still our density. So it still maintains the same density, which is C naught. Then knowing that this is the formula, this is the unit. The unit is kilogram per meter cube. Per meter cube. And then we have the volumetric flow rate. Let's say here, this is going on, let's say it's Q naught, then meter cube per second. So these are the units now. So now you have this dissolved salt. That is moving. There's a movement. There's a flow. So let's say from here now we can also calculate the mass flow rate. Now how do we determine mass flow rate? Mass flow rate by definition is equal to change in mass with respect to time. We say that is mass flow rate. Mass flow rate, flow rate is equal to change in mass with change with time, with respect to time, is equal to density So density times what? Times volumetric what? Flow rate. So this by definition, mass flow rate gives you this. dm over dt times is equal to density times volumetric flow rate. So first of all, we need to calculate the input source, mass of the input source, or the mass flow rate of the input source, and then we also need to calculate the mass flow rate of the output source. So now let's see mass flow rate, mass flow rate of of the of the source, input source, input source will give you C1 times volumetric flow rate, C1 times volumetric flow rate, which is Q1. And let's say now we want to know the unit of this mass flow rate. We can now say the unit of the density, which is kilogram per meter cube. We multiply the unit of volumetric flow rate, which is meter cube per second. So we're going to have kilogram over meter cube times the unit of volumetric flow, which is meter cube over second. So that this meter cube will cancel each other. So we're going to have it in form of kilogram per second. So that's the unit of volumetric, that's the unit of mass flow rate. So mass flow rate now of the input source will give you this C1 times Q1 is equal to kilogram per second. So that you should also take note of the units of mass flow rate, unit of volumetric flow rate, unit of what molar flow rate. So these three, they have different units. So like the one of volumetric flow rate is here on the board, meter cube per second. Then the one of the mass flow rate is in kilogram per second. Then the molar flow rate is in kilomole or mole per second, or you can say mole per hour. So now we over to mass flow rate. Mass flow rate, mass flow rate of the output source. The output source will give you, here's the output source. Will give you C naught times Q naught. You have C naught times what? Q naught. So the same thing goes. You have the unit kilogram per meter cube times meter cube per second. So that this will cancel this. So you still have the same unit as kilogram per second. So if you go to a textbooks in chemical engineering like Cosin and Richardson volume 1, if you go to Cosin and Richardson volume 2, most of you see volume 1, you see that most of the questions in that textbook, you will come across units of this form, kilogram per second. So whenever you come across a unit like this, which is kilogram per second, just know that that thing is in, just know that it is mass flow rate. The mass flow rate is given from that question. So you use it and then do your calculation. So now, I told you that this C is density. And how do we get this density? Density is obtained, is gotten, the formula of density, you can see it in physics. You see it in mathematics. So we all know that density will give you mass over what? Volume. So now, what I'm going to do now, I also need to get the mass flow rate of the accumulated source. So before we come to that aspect, or before I come to that aspect, let me write the general energy con, conservation with equation. Energy conservation equation. Then we have source output is equal to source input. Then you have a plus salt generation, then minus salt consumption, then minus salt accumulation, minus salt accumulation. So this is the equation now. So since we are dealing on mass flow rate, so we will now present it in form of mass flow rate. Now, like we're going to present it in this form, like mass flow rate, flow rate of output salt is equal to mass flow rate of input salt, then plus mass flow rate of generated salt. Then you have minus mass flow rate of salt consumption. Then minus mass flow rate of accumulated salt, This is what I'm going to get. Now we are going to look at some basic simplifying assumptions. So those simplifying assumptions, we now look at the the system is operated with a volumetric flow rate. Then the same system will tell you has a volume, has a constant mass volume, has a constant volume. Let's say the volume of the tank V. We also need to look at another assumption. The assumption is no generation or consumption by chemical reaction. So these are the simplifying. We will look at the simplifying assumptions. Before we come to that aspect, we need to calculate the mass flow rate. Just the way I did the mass, how to get mass flow rate of the input source, and then for the output source, then I need to calculate the mass flow rate of the accumulated source. So now it will be like this. It will now be like the mass flow rate of accumulated what source. It will be equal to, it will give you equal to, sorry, so let me just bring it up, let me bring it down a bit. Let it not be as if they are together. So now I have mass flow rate of accumulated source. I have now it will now be GM, change the mass over time. This is change the mass over time. So there's something you need to know about accumulation. Whenever you are asked to calculate accumulation now will be with respect to time. So whatever you are getting, you divide it by time. Just like you have the M. This M represents mass. We all know that. How do we get mass? We know that density then CT, C. Let's use C to represent density. We give you mass over what? Volume. Mass over volume. Same thing as M over V. So we are using C to represent density. So now, from here, our M will give you CV, that is density times volume. So you will now put it here. You now have D into CV over what? DT. So you will substitute, you will get it in this form. So this is how you get your mass flow rate of accumulated salt. Now, before we come to this aspect, we will need to look at the simplifying assumptions. So the simplifying assumptions, we have one, we need to look at simplifying assumptions. Assumption. We need to look at this simplifying assumption. One, you must the system operates with a steady state, operates on a state, a steady state. Two, the system so so these are the assumptions now. The system operates on a steady state. The system operates with a volumetric flow. The tank contains a volume of V meter cube. Then no generation by chemical reaction. So now these are the simplifying assumptions. So from here, since we have gotten our mass flow rate of the input source, we have also gotten our mass flow rate of the output source, then the one of accumulated source. So from here, we are going to use this formula, using this the general energy conservation equation. We are going to use it to derive an equation. So now we are going to use it now. Using this now, mass flow rate of output source is equal to mass flow rate of input source plus mass flow rate of generated source minus mass flow rate of salt consumption minus mass flow rate of accumulated salt. So since there is no chemical reaction now, let's say there is no chemical reaction, then your mass flow rate of generated salt and the mass flow rate of salt consumption becomes what? Zero. So now we are going to use it now to calculate. Now let's see. Once you do that, the equation now will be like this. The mass flow rate of the input salt here, C1 multiplied by Q. That's the volumetric flow rate. Then you have mass flow rate of the output salt, which is equal to Q C naught times Q. So now this is the container. You have your C1, a function of T, which is kilogram per meter cube. Then you have your Q, volumetric flow rate, which is meter cube per second. Then you have the output source. This is the input source, and this is the output source. You have the density. The density is C naught, the output source. You also have the volumetric flow rate, meter cube per second. So don't use in the input source, don't use Q1 here, and at the output source, don't use Q naught. Still make use of our Q is Q. So now from here, looking at the energy, the general energy conservation equation, you have this. So now, since no chemical reaction involved yet, so you both your mass flow rate of the generated salt and the mass flow rate of the salt consumption becomes zero. So once it's zero, you're going to have the equation in this form. It will now be like mass flow rate. You have mass flow rate of output salt. Output salt will give you mass mass flow rate. Mass flow rate of input salt. Then you have this one is zero. This one is zero. So you have minus mass flow rate of accumulated salt. So your accumulation is within the tank. This is a tank. Contains a dissolved salt. So you have your accumulator at this point here. That's why I have mass flow rate of accumulated salts. So now, mathematically, I want to make a mass flow rate of accumulated salt the subject formula. So if I make it the subject formula, I'm going to have mass flow rate of accumulated salt will give you mass flow rate of the input salt minus mass flow rate of the output salt. So this is what I'm going to get now. If you take your mass flow rate of generated salt and mass flow rate of salt consumption zero, you're going to have the equation here. This is what I'm going to get. Then mathematically, if you arrange the equation, I'm making mass flow rate of accumulated salt the subject formula. You're going to get the equation in this form. So from here now, we're going to put down all these things here that we wrote. We're going to put it down in this equation to form an equation. So now we're going to look at the value for mass flow rate of accumulated salts. So to give you dCV over dt, so equal to the mass flow rate of input salts. The input salt now is Q C1 times Q, then minus mass flow rate of the output salt. It will give you minus C naught Q. So now we have gotten the equation now. This is an equation. We have gotten an equation. Let's say this one now. This one now is equation 1. And this one now is equation what? 2. So from here, we can see this one is equation what? 3. We have this equation 3. So now from here, you see that this d bracket cv change in bracket cv over dt will give you c1 q minus c naught q. Now we're going to look at it at a steady state. At at a steady state, then we'll have the equation like this: d into, instead of you to write c now, we'll now see c s v. You have c s v over the t. That is equal to c 1x cube minus c 0x cube. So this one now, we'll take this one as equation what? 4. So at steady state, this is what I'm going to get. This x represents steady state. Yes, sir. So now we will now say this one is equation 4. See, equation, you say equation 3 minus equation 4. Equation 4. So now our equation 3 now is this. So we're going to say d into cv over the t minus d into csv over the t will give you, then our equation 3 here, we have on the right hand side we have c1 cube minus c0 cube. Then we are subtracting it from equation 4. Equation 4 from the right hand side, you have minus, you have to put it in bracket. Since we are subtracting it, you say minus bracket c1 x cube minus cos cube. This is what we are going to get. We're going to form another equation. So let me clean up this board. We are going to factorize now. You see that something is common here. We have dv over the t is here. I also have dv over the t is here. So factorize. Factorize, we're going to have v dv is certain as vd over the t. So if you remove vd over the t, you're going to have c. You have c minus the same thing here, you're going to have cs. So it's equal to c1 cube minus c0 cube. Then we are going to open up this bracket. Use this minus sign to open this bracket. If you open it up, it will be minus times c1x cube. It will give you minus c1x cube. Then you have minus times this minus is plus. So times cos cube will give you plus cos cube. So this is what I'm going to get now. So at the end of the day, you're going to do what? They're going to subtract, they're going to add up ix together, os together. So we add it up, they're going to get it in this form. Let's say we have v d over dt. Then you have c minus cs. Then you have equal to, you have this c1 cube minus c1s cube. Then you have minus c0 cube. Then you have plus cos cube. This is what I'm going to get. So now, but there's something you need to know, like mass flow rate of accumulated salt. Instead of me to write CV, because the density here, from the tank we have accumulated salt. The density here is C0. So I will now replace it with C0. It will be C0 V. So it's supposed to be C0 S, C0 S V as steady state. This is what I'm going to get. So it will now be here to be C0 S V. Then here I need to effect the correction here. I have COX. This is what I'm going to get because the density of the accumulator salt inside the tank is C naught. So instead of me to use C, I will use C naught. So now, then here also you give me COS. I have COS. So now I have added I's together and then O's together. So from here I have C1. I have C1 minus CIS. Then you factorize. You factorize it, you're going to have this times Q because this Q is common here. So you factorize it mathematically. You do the same thing with this one. You say minus, I have Q here, minus Q into C naught. Then this one will be like minus COS. Then you close it this way, COS. So now this one now will be this one now will be like O because this one now is equation 3. So equation 3 multiplied by it will be COV, then minus this one that is here now. So that is here is the one of equation 4. It will now be COS because this one now is at steady state. The first one is not at steady state. So you're going to have COV. So here will be CO. Then you have CO, not S. CO. Because this first one now, equation 3 is not at steady state. So at steady state here you have COSV. So you do equation 3 minus equation 4. Equation 3 now will be D over DOV minus D over DOSV over dt. Because this one now is at steady state. That's why I'm having X here. So if you subtract, you're going to get it in this form. So knowing that we have dv over dt here, we also have dv over dt here. So you know what? You factorize. When you factorize, you're going to have it this way, dv over dt. You remove dv over dt here, you have co here. So then coming here, if you remove dv over dt, you're going to have cos. You have COS. Then here COS. So that's the correction. So from here now, I have a V d over dt into CO minus COS. Then I have equal to C1 minus C1x times multiplied by Q minus Q into CO minus COS. So now, what I'm going to do now, I'm going to divide 2 by what? Q. See, divide 2 by what? Q. If I divide 2 by Q, I'm going to have it this way. I have V over Q d over dt, then into CO minus COS. Then it will be equal to Q into C1 minus CIS or C1x minus bracket CO minus COS times Q. So that this Q will cancel this Q because I'm dividing all 2 by what? Q. So the Q will cancel this. So we are going to have another equation. V over Q into CO minus COS equal to, you have equal to C1 minus C1 x. Then we have minus into CO minus COS. This is what you're going to get. You're going to get the equation like this. So now, let's say let this time constant tau equal to V over what? Q. V over Q. This V represents volume. Q stands for the volumetric flow rate. So like if you want to know the unit of this tau, which is time constant, we're going to use the unit of volume here. You say volume is the meter cube divided by the unit of volumetric flow rate, which is meter cube over seconds. So if you change this now to multiplication sign, you're going to have meter cube times this will go up, this will come down, times x over what? Meter cube. So this meter cube cancel this meter cube. You're going to have this. You're going to have it in seconds, which is what? X. So that's the unit of this. I'll give you seconds. So from here, we're going to put it here. This multiplied by CO. Oh, there is a mistake. Yeah. So it will be V over Q times D over dt times D over dt. So we are going to do the same thing. So multiply by V over Q times D over dt. So our V over Q is equal to what? Tau. So we are going to have it as this. Tau into CO minus COS. Then is equal to C1 minus C1S. Then multiply by CO minus COS. This is what I'm going to get. So finally, I'm going to get in this form. This is the equation I'm going to get now. So this equation now, let's say that equation was equation 4. So let's say this one is equation what? 5. We call this equation 5. Yes, because we started from here. Divide 2 by Q. I have V over Q, D over dt, multiply by CO minus COS equal to this Q into C1 minus C1S. They are divided by Q. They cancel this Q, cancel this Q. Minus by CO minus COS times Q. This Q cancel this Q. So we're going to get it here. So now select this equal to V over Q, which means this thing represents time constant. Is our time constant. So from here, I was able to get the unit of this time constant as seconds. So from here, I also see V over Q is equal to this. So I say this D over dt multiplied by this is equal to C1 minus C1S minus the bracket CO minus COS. So now I've gotten equation 5 now. So from here I'm going to introduce derivation variables. So derivation variables. So when I introduce derivation variable, I'm going to have here C1 minus C1S will give you, it will give you C1 prime of what? T. So if I do the same thing here, this one I have CO minus COS will give me CO prime of what? T. So from here now, let me call this one equation 6. And then let me call this equation 7. So what I'm going to do, I say substitute equation 6 and 7 into what? Into 5. So into equation 5. Then I'll do that. From my equation 5, I'm having this tau d over dt. Then multiply by C0 minus COS to give you CO dot of what? T. Then is equal to This one C1 minus C1 S will give you C1 prime of what? T. Then I have for minus CO minus COS, they give you minus CO minus COS will give you CO prime of what? T. So this is what I'm going to get. So you see that you're going to have a differential equation now. If you open up this bracket now, if you multiply this by this, you're going to have the equation of this form. You have time constant d over the t times this will give you d c naught prime of t over the t. So is equal to c 1 prime of t minus c naught prime of what? T. So now you will now move, this one is minus c naught prime of t. So if you bring it here, it will be tau d c naught prime of t over dt. Then becomes plus c naught prime of t will give you c1 prime of t. So you see that we have derived first order system of a mixing process. And I told you that the equation must correspond to this equation, which is a1 dx over dt. That's the x with respect to time. So plus a naught plus a2 x is equal to k multiplied by function of what? T. So you see that this equation now will correspond with this equation. So it corresponds. So from here now, we're going to look at our aim of doing this thing now is to obtain a transfer function. So what I'm doing now is to derive an equation. And what's the name of that equation? Transfer function. So now, having this, so before I come to this is a differential equation now. So what I'm going to do is that I'm going to take a condition now, initial condition as c prime of 0, c prime, c 0 prime of 0. Let's say is equal to 0. Let's take this as initial condition. So now look, see this is differential equation. Let's say this is equation what? Equation 8. This is equation 8 now. So we're going to take Laplace transformation of equation 8. So take Laplace transformation. Take Laplace transform of equation 8. If you take Laplace transform of equation 8, meaning you are going to take the Laplace transform on the left hand side and also the Laplace transform on the right hand side. So see, we are going to do it this way now. So say this time constant is constant. So you're going to have time constant, then multiply by Laplace transformation of d c naught prime of t over the t. Then it will give you the same plus Laplace transformation of c naught prime of t. You still going to do it at the right hand side, taking Laplace transform on both sides. So now this one now is first order. This first order, like I did in our previous class, I derived the formula for obtaining Laplace transformation of first order, second order, and third order. So this one now is the Laplace transformation of dc naught prime of 0 of t over the t will give you s c naught prime of what? S minus c naught prime of what? 0. This is what I'm going to get. If you take Laplace transformation of this is first order, it will give you this. From here now, we're going to substitute it into this equation. Then from there we solved. This Laplace transformation of this first order, you substitute it here in this equation. We're going to have the time constant multiplying the Laplace transformation of this first order, which is x c naught prime of what x minus c naught prime of what 0. Then with the Laplace transformation of c naught prime of t will be transformed to what? To c naught prime of what x, because we are transforming this t function to x function. So if you do the same thing on the right hand side, the Laplace transformation of c1 prime of t, it will be transformed to c1 prime of what x. So going to is equal to c1 prime of what x. So it will transform. So finally, you now I'm going to apply the initial condition. The initial condition is my c naught prime of t is equal to 0. So I'll put it here. I have tau bracket s c naught prime of x minus 0. Then I have plus c naught prime of what? X is equal to c 1 prime of what? X. So what I'm going to do now, I'm going to now open up this bracket with this time constant. So, but this one now is the same thing as this multiplied by this minus this will give you x c naught prime of what? X. So plus c naught prime of what? X equal to c 1 prime of what? X. So finally, if you open up this bracket with this, you're going to have tau x c naught prime of what? X plus c o prime of what? X is equal to c 1 prime of what? X. So we're going to go now. So now, you're looking at this now, something is common. C naught prime of x is here. I also have c naught prime of x here. So I'll factorize. If I factorize, I'm going to have c naught prime of x. If I factorize, I'm going to have tau x plus what? 1. This one will be duplicate. This one will become what? 1. So that if you open up this bracket with this c naught prime of x, with this, the one that with the bracket, if you open up this bracket with this one, you're going to have this thing back. That is c naught prime of x times tau x will give you tau x c naught prime of x. Then multiply this by this, you're going to have c naught prime of what? X is equal to c1 prime of what? X. So now, what I'm going to do now is divide 2 by tau x plus what? 1. So we're going to have c naught prime of what? X. Then I have tau x plus what? 1. So it's equal to c1 prime of what? X. So that this tau x plus 1 will cancel each other. I have tau x plus what? 1. So that I'm going to have c naught prime of x equal to c1 prime of x over tau x plus what? 1. So now, the next thing I'm going to do now, because I want to obtain an equation. So let me multiply. So multiply 1 over c1 prime of x from both sides. From both sides. That is from both the right hand side and the left hand side. So here is c0 prime of x over c1 prime of x to give you c1 prime of x over tau x plus what? 1 multiplied by 1 over c1 prime of what? X divided by this, because we are multiplying both sides by 1 over c1 prime of x. So this will cancel this. We are going to have 1 over tau x plus what? 1. So that we're going to have c naught prime of x over c1 prime of what? X will give you 1 over tau x plus 1. So this is an equation now. This is an equation I need to get. This is what we call transfer function. So, and this transfer function is equivalent to where to y of x over s of x will give you give you k p over tau p tau x plus what 1. This is the general formula for this one. I'll give you general transfer function. So this is known as what? G of what? X. G of x is known as the general transfer function. So thank you for listening to or watching my YouTube channel. Please always endeavor to subscribe to my YouTube channel. This is the only way YouTube will recognize my channel. So please, as you subscribe, don't fail to press the like button. So as you do so, thank you very much and God bless you. Have a nice day.